In 1915, Albert Einstein published his general theory of relativity, fundamentally changing how we understand gravity, space, and time. Within a year, a German physicist named Karl Schwarzschild discovered something extraordinary hidden within Einstein's equations, a mathematical solution that predicted regions of space so warped by gravity that nothing, not even light itself, could escape. This discovery laid the foundation for what we now call black holes, yet it also introduced one of the most profound and counterintuitive ideas in all of physics. When most people hear the term black hole, they imagine a massive, incredibly dense object floating in space, like an ultra-heavy planet or a cosmic vacuum cleaner, sucking everything around it into oblivion. However, this mental picture, while convenient and widespread, misses something crucial about what black holes actually are. The reality is far stranger and more fascinating than the simplified stories we often tell ourselves. A black hole is a region in space-time where gravity becomes so extraordinarily intense that the fabric of the universe itself fundamentally transforms. According to general relativity, massive objects bend and warp the space-time around them. Much like a heavy ball placed on a stretched rubber sheet creates a depression. The more massive an object is and the smaller its volume, the more extreme this warping becomes. When a star with a core more than about 2.5 times the mass of our Sun reaches the end of its life and exhausts its nuclear fuel, it can no longer support itself against its own gravitational pull. The core collapses catastrophically inward in what astronomers call a supernova explosion, with the outer layers blasting away into space while the core continues to compress. If this collapsing core is massive enough, it keeps collapsing past the point where it could form a neutron star, which is already incredibly dense, with matter packed so tightly that a teaspoon would weigh billions of tons on Earth. As the core continues collapsing beyond this threshold, something remarkable happens. The escape velocity at its surface, the speed needed for anything to break free from its gravitational grip, approaches and then exceeds the speed of light itself. The escape velocity formula shows that as mass becomes concentrated in a smaller and smaller radius, the velocity required to escape grows larger. At a certain critical radius, now called the Schwarzschild radius in honor of Karl Schwarzschild, the escape velocity exactly equals the speed of light. Since nothing in our universe can travel faster than light, according to Einstein's special relativity, this creates an absolute boundary, a point of no return. This boundary is what physicists call the event horizon, and it marks the surface of what we call a black hole. Beyond this horizon, space-time is so severely warped that all paths, even those of light rays, curve inward toward the center. There are literally no trajectories that lead back out into the wider universe. Here is where our understanding must shift dramatically. When we say nothing can escape, including light, we are not describing an incredibly dense ball of matter sitting in space. Instead, we are describing a region of space-time itself that has become fundamentally disconnected from the rest of the universe in terms of causal influence. The event horizon is not a physical surface made of material or energy. It is an invisible boundary in space itself, a point of no return defined purely by geometry and gravity. If you could somehow approach a stellar mass black hole, one formed from a collapsed star roughly 10 times the mass of our Sun, The event horizon would have a radius of approximately 30 kilometers. But when you reach that boundary, you would encounter no wall, no shell, no barrier of any kind. You would find only empty space, albeit space so warped that its properties have become alien to our everyday experience. This realization forces us to reconsider what we mean when we use the word object. Typically, an object is something made of matter, something with a surface you could touch if you got close enough, something that occupies space in a tangible way. A rock is an object. A star is an object. Even a cloud of gas drifting through interstellar space could be called an object in a loose sense. But a black hole challenges this definition at its core. The event horizon contains no matter, no substance, no stuff at all. It is simply a location in space beyond which the rules change completely. Below the event horizon, at the very center of the black hole, general relativity predicts the existence of what physicists call a singularity. This is theoretically a point of zero volume and infinite density where all the mass of the collapsed star has been compressed. At the singularity, the curvature of spacetime becomes infinite, and our current understanding of physics breaks down entirely. The equations that describe gravity, matter, and energy all produce infinities and cease to make reliable predictions. However, the singularity is hidden from the outside universe by the event horizon, a feature that physicist Roger Penrose called cosmic censorship. We cannot observe the singularity directly, and nothing that happens there can send information back out to us. For all practical purposes, when we talk about interacting with a black hole, detecting a black hole, or even falling into a black hole, we are really talking about interacting with the event horizon and the region of warped spacetime around it. The singularity itself remains forever sealed away from observation. This leads to a profound shift in perspective. Perhaps it is more accurate to think of a black hole not as a thing, not as an object, but as a place. It is a region of space, a volume of the universe where the laws of physics as we experience them have been pushed to their absolute limits and beyond. Imagine for a moment that you could mark out a spherical region of empty space right now, perhaps the size of a room. That region is not an object. It is simply a location, a piece of space itself. Now, imagine that the properties of that region change dramatically due to the presence of mass nearby. The geometry would warp, time would flow differently, and the behavior of light and matter within it would become strange. This is closer to what a black hole actually represents. Space-time itself, transformed by gravity into something that behaves in ways that seem impossible by everyday standards. The black hole is the space, not something sitting in the space. This distinction may seem subtle, but it has profound implications for how we understand what happens when matter falls in, why nothing can escape, and even what the interior of a black hole might be like. The common depiction of black holes as cosmic vacuum cleaners is also misleading. A black hole does not reach out and grab things from afar any more than any other massive object would. If our sun were somehow magically replaced with a black hole of exactly the same mass, Earth would continue orbiting at the same distance with the same orbital period, experiencing the same gravitational pull. The gravitational field far from a black hole is no different from that of any other object with the same mass. The unique and extreme properties only emerge when you get close enough to the event horizon that the warping of space-time becomes severe. At great distances, a black hole's gravity follows the same inverse square law as any star or planet. It is only near the event horizon that everything changes, where space and time become so distorted that our intuitions completely fail us. Throughout this exploration, we will challenge the common assumptions about black holes and dig deeper into what modern physics actually tells us about these extraordinary regions of space-time. We will examine why the popular definition of a black hole, while capturing something important, also leads us astray in fundamental ways. We will explore what the event horizon really is, not as a surface or barrier, but as a geometric feature of space-time itself. We will consider what it would be like to approach and cross this boundary, and why the experience would be far stranger than simply hitting an invisible wall. Most importantly, we will grapple with the question posed at the very beginning. What if a black hole is not a thing at all, but rather a place, a location in the universe where reality itself has been fundamentally transformed by the overwhelming power of gravity? This shift in understanding, from object to place, from thing to region of space, is essential if we want to truly comprehend one of the most extreme and fascinating phenomena that nature has to offer in our vast and mysterious cosmos, where the very fabric of existence bends under forces beyond our everyday comprehension. Now that we have begun questioning whether a black hole is truly a thing, or something far more abstract, we need to establish what most people mean when they use the term black hole. The popular definition, repeated in textbooks, documentaries, and science articles around the world, describes a black hole as a region of space containing matter so incredibly dense that nothing, not even light itself, can escape from its gravitational pull. This description has become the standard way of introducing black holes to students, curious minds, and anyone fascinated by the mysteries of the cosmos. You have probably heard some variation of it yourself. A black hole is an object with gravity so powerful that it traps everything, including the fastest thing in the universe, light. This definition captures something essential and true about black holes, yet it also carries hidden implications that can mislead us about their fundamental nature. To understand why this definition works and where it falls short, we need to dive deeper into what physicists mean when they formally define a black hole within the framework of general relativity. Albert Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity by showing that what we experience as gravitational force is actually the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets create dips and warps in the fabric of space-time, and other objects moving through that warped space follow curved paths that we interpret as orbits or falling motion. The mathematics of general relativity provides precise equations, known as the Einstein field equations, that describe how matter and energy curve space-time, and how that curvature affects the motion of everything from particles to light rays. When physicists use these equations to model extremely dense concentrations of matter, they discover solutions that predict the existence of black holes. The simplest and most famous of these solutions is called the Schwarzschild solution, named after Karl Schwarzschild, who derived it in 1916, just months after Einstein published his theory. The Schwarzschild solution describes the space-time geometry around a non-rotating spherical mass. For most masses, like stars or planets, this solution simply tells us how space-time curves around them in a relatively gentle way. But when you pack enough mass into a small enough volume, something dramatic happens. The curvature becomes so extreme that it creates a boundary in space-time, a spherical surface of a specific radius beyond which the escape velocity exceeds the speed of light. This boundary is the event horizon, and its radius is called the Schwarzschild radius. The Schwarzschild radius depends only on the mass of the object. For our Sun, which has a mass of about 2 times 10 to the power of 30 kilograms, the Schwarzschild radius is approximately 3 kilometers. This means that if you could somehow compress all the mass of the Sun into a sphere with a radius of 3 kilometers or less, it would form a black hole. The Sun's actual radius is about 700,000 kilometers, so it is nowhere close to forming a black hole under normal circumstances. For Earth, the Schwarzschild radius is about 9 millimeters. If you compressed our entire planet into a sphere smaller than a marble, it would become a black hole. These examples illustrate a crucial point. Becoming a black hole is not just about having a lot of mass. It is about concentrating that mass into an extraordinarily small volume so that the warping of space-time becomes extreme enough to create an event horizon. The popular definition describes a black hole as something so dense that light cannot escape, and this is accurate in a specific sense. Light, traveling at 300,000 kilometers per second, follows the straightest possible paths through space-time, which physicists call geodesics. In flat, uncurved space-time far from any masses, these paths are straight lines. Near massive objects, space-time curves, and light follows curved paths, which is why we observe phenomena like gravitational lensing, where light from distant stars bends around massive galaxies. At the event horizon of a black hole, the curvature has become so intense that even light rays aimed directly outward curve back inward. There are no outgoing geodesics, no escape paths for light or anything else. This is what we mean when we say nothing can escape. The geometry of space-time itself prevents any object or signal from moving from inside the event horizon to the outside universe. This aspect of the definition is tremendously important and captures the single most distinctive feature of black holes. The event horizon represents a one-way boundary in space-time. Matter, light, information, anything at all can cross the horizon going inward, but nothing can cross it going outward. Once you pass through the event horizon, your future is determined. All possible paths lead further inward toward the singularity at the center. This is not because some force pulls you inward, although tidal forces do become extreme near smaller black holes. Rather, it is because the structure of space-time itself has changed so fundamentally that every direction you could possibly move, every trajectory you could follow, points inward. The event horizon is a point of no return, defined purely by geometry, not by any physical barrier or surface made of matter. However, the popular definition also carries problematic implications, particularly when it describes a black hole as a dense object. This phrasing suggests that a black hole is a thing, a piece of matter, something solid, or at least tangible, sitting in space. It evokes images of an incredibly compact star, or perhaps a ball of super-dense material. But this mental model conflicts with what general relativity actually tells us about the structure of a black hole. The event horizon itself is not made of anything. It contains no matter, no energy, no particles, no fields. It is simply a boundary in spacetime, a geometric feature that marks the location beyond which escape becomes impossible. If you could approach the event horizon of a large black hole, one with a mass millions or billions of times that of the Sun, you would find that the tidal forces at the horizon are actually quite gentle. You could cross it without feeling anything unusual at that precise moment. There is no surface to collide with, no wall to hit. The matter that originally formed the black hole, the collapsing core of a massive star, for example, does not stop at the event horizon. According to general relativity, it continues collapsing inward past the horizon, ultimately reaching the singularity at the center where density becomes infinite, and the curvature of space-time becomes infinite as well. The singularity is where the equations of general relativity break down and produce mathematical infinities that signal the theory's limits. Most physicists believe that a complete theory of quantum gravity, which we do not yet have, would replace the singularity with something less pathological. But whatever exists at the very center, it is hidden from the outside universe by the event horizon. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that singularities are always hidden behind event horizons and can never be observed directly from the outside. So when we define a black hole using the popular description, we capture the essential truth that it is a region from which nothing can escape. But we risk giving the impression that the event horizon itself is a dense object. This confusion matters because it affects how we think about what happens when something falls into a black hole, what it would be like to approach or cross the event horizon, and even what the inside of a black hole might contain. If we think of a black hole as a solid object with a surface, we might expect that falling into one would involve hitting that surface, experiencing some kind of collision or barrier. But the reality, as we will explore in the coming parts, is far stranger and more subtle than that. The definition of a black hole within general relativity is both precise and profound. It is a region of space-time bounded by an event horizon within which the escape velocity exceeds the speed of light, and inside which all time-like and light-like paths lead inevitably toward a central singularity. This definition emphasizes that black holes are fundamentally about space-time geometry rather than material substance. They are solutions to the equations that describe how mass and energy warp the fabric of the universe. Understanding this distinction is crucial as we continue exploring what black holes truly are, how they behave, and why thinking of them as places rather than things opens up a clearer and more accurate picture of one of nature's most extreme phenomena in the vast cosmos we inhabit. Having established what the popular definition of a black hole states, that it is a region so dense that not even light can escape, we now need to evaluate this definition more carefully. Every definition carries strengths and weaknesses, aspects that illuminate truth and aspects that potentially mislead. The popular description of black holes, despite its simplifications, captures something profoundly correct and observationally verifiable about these mysterious objects in our universe. The good part of this definition, the element that aligns perfectly with both theory and observation, is its emphasis on the absolute darkness of black holes and the inescapable nature of their gravitational grip once you cross a certain boundary. The most important truth embedded in the popular definition is this: black holes are completely and utterly dark. They emit no light of their own from within the event horizon. No photons escape. No electromagnetic radiation of any wavelength, whether radio waves, infrared, visible light, ultraviolet, X-rays, or gamma rays, can make the journey from inside the event horizon to the outside universe. This absolute darkness is not merely a matter of being dim or faint, like a distant star too far away to see clearly. Rather, it represents a fundamental barrier imposed by the geometry of space-time itself. Once light crosses the event horizon going inward, the structure of space-time ensures that all future paths lead further inward toward the singularity. There are no outward trajectories, no escape routes, no loopholes in the mathematics that would allow even a single photon to break free. This prediction of general relativity has profound observational consequences that astronomers have exploited to detect and study black holes throughout the universe. Since black holes themselves emit no light, they cannot be seen directly through telescopes in the way we observe stars, galaxies, or nebulae. You cannot point a telescope at a region of space and see a black hole glowing against the cosmic background. Instead, astronomers must rely on indirect detection methods that observe the effects black holes have on their surroundings. These methods have become increasingly sophisticated over the past several decades, providing overwhelming evidence that black holes exist and confirming the theoretical predictions made by Einstein's equations nearly a century before their observational discovery. One of the most powerful methods for detecting black holes involves observing binary star systems where one member is visible and the other is invisible, yet clearly massive. In such systems, the visible star orbits around an unseen companion, and by measuring the orbital period, the speed of the visible star, and the characteristics of its motion, astronomers can calculate the mass of the invisible object using Newton's laws of motion and gravity. When that mass exceeds the theoretical maximum for a neutron star, approximately 3 solar masses, the invisible companion must be something else, a black hole. The first strong candidate for a stellar mass black hole, an object called Cygnus X1, was identified through precisely this method in the 1970s. Astronomers observed a blue supergiant star orbiting an invisible companion with a mass estimated at around 15 solar masses, far too heavy to be a neutron star and therefore almost certainly a black hole. But the detection method goes beyond simply finding invisible, massive companions. The darkness of black holes becomes even more apparent when we observe what happens to matter falling toward them. As gas from a companion star or from the surrounding interstellar medium falls toward a black hole, it does not simply vanish silently into the darkness. Instead, the infalling matter typically forms an accretion disk, a swirling disk of gas and dust that orbits the black hole before eventually crossing the event horizon. The material in these accretion disks moves at tremendous speeds, often reaching significant fractions of the speed of light. Friction and collisions between particles in the disk heat the gas to millions of degrees. At these extreme temperatures, the gas emits intense radiation, particularly in the X-ray portion of the electromagnetic spectrum. This X-ray emission from the accretion disk provides one of the most reliable signatures of black holes. X-ray telescopes in space, such as the Chandra X-ray Observatory and XMM Newton, have detected thousands of X-ray sources throughout our galaxy and beyond. Many of these sources exhibit characteristics consistent with matter spiraling into black holes. They show rapid variability in brightness, spectral features indicating gas moving at relativistic speeds, and energy outputs that require extremely compact and massive objects to explain. The accretion disks around black holes can be extraordinarily luminous, sometimes outshining entire galaxies, despite the relatively tiny volume of space they occupy. Yet the black hole itself, the region inside the event horizon, contributes nothing to this light show. It remains perfectly dark, a shadow at the center of the cosmic fireworks. Recent advances in observational astronomy have even allowed scientists to image the shadow of a black hole directly. In 2019, the Event Horizon Telescope collaboration announced the first ever image of a black hole's event horizon, or more precisely, the shadow cast by the event horizon against the bright background of its accretion disk. The target was the supermassive black hole at the center of the galaxy, Messier 87, located about 55 million light-years from Earth. By combining data from radio telescopes around the globe to create a virtual Earth-sized telescope, astronomers captured an image showing a bright ring of emission surrounding a dark circular region. The dark region is the black hole's shadow, the area from which no light can escape. The bright ring is emission from the accretion disk and from photons that have been bent around the black hole by its intense gravity. This historic image confirmed what general relativity had predicted. Black holes cast shadows, regions of darkness defined by the event horizon and the photon sphere around it, where light can orbit the black hole in unstable circular paths. The size and shape of the shadow match theoretical predictions with remarkable accuracy, providing one of the strongest confirmations yet that Einstein's equations correctly describe these extreme objects. The shadow exists precisely because nothing, absolutely nothing, can escape from within the event horizon. The darkness is total and permanent, an indelible feature of black hole physics. Beyond electromagnetic observations, the 21st century has witnessed the birth of gravitational wave astronomy, which has revolutionized black hole detection. When two black holes orbit each other and eventually merge, they create ripples in the fabric of space-time itself called gravitational waves. These waves propagate outward at the speed of light, carrying information about the masses, spins, and orbital characteristics of the merging black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves from a black hole merger. This groundbreaking observation not only confirmed another prediction of general relativity, but also opened an entirely new window for observing black holes. Since then, LIGO and its partner detectors have observed dozens of black hole mergers, revealing a population of black holes with a wide range of masses and properties. The popular definition captures this essential truth perfectly. Black holes are regions from which nothing escapes. This inescapability is not a matter of degree or probability. It is absolute. The event horizon marks a true point of no return, a boundary beyond which the causal structure of space-time itself prevents any signal, object, or influence from reaching the external universe. Every observation we have made, from X-ray binaries to gravitational waves to shadow images, confirms this fundamental property. The darkness is real, complete, and permanent. This is the good part of the popular definition, the core truth that makes black holes so fascinating, so extreme, and so unlike anything else in the cosmos we study and explore with our instruments and theories. Having established the good aspects of how the popular definition presents a black hole as a perfectly dark region where nothing escapes, not even light, we now need to confront a critical misconception that arises from the same definition. The widespread image of a black hole as a dense physical object or a solid sphere sitting in space is fundamentally misleading when it comes to both the structure and essence of black holes. This misunderstanding persists not only in popular culture, but even in media, entertainment, and casual explanations in educational settings around the world. Addressing this misconception clarifies what is truly happening at a black hole's boundary and why thinking of black holes as objects severely limits our understanding of their true nature and behavior in the universe. The definition implying that a black hole consists of a dense object, much like a ball of matter compressed into an impossibly small volume, suggests there must be a physical surface you could encounter if you approached it closely enough. This image is so persuasive and deeply ingrained that many people imagine a black hole as a sort of cosmic sphere, densely packed with particles and fields, perhaps with a hard surface, or at least some tangible substance that defines its boundary and separates inside from outside. Yet, in actual fact, no such surface exists at the event horizon whatsoever. You would not collide with any material upon reaching this region. The reality, revealed by general relativity and confirmed through astronomical observations over decades of careful study, is that the event horizon is not made of anything at all. Instead, it is a location within space-time, a boundary defined solely by gravity and the mathematical properties of the universe, as described by Einstein's field equations that govern how mass and energy curve the fabric of space and time. This conceptual error matters deeply for how we interpret the physics of black holes and their interaction with the surrounding universe, and all the matter and energy that approaches them. If the event horizon were a physical surface made of some exotic material or energy field, we might expect infalling material to pile up atop it, forming a layer or structure resembling a planet or star with a crust or core that could be studied. Many early astrophysical models, developed in the decades following Einstein's publication of general relativity, tried to fit black holes into familiar categories, picturing them like neutron stars but with higher density and more extreme compactness, concentrated in a smaller volume. However, no light or electromagnetic radiation is seen reflecting off the event horizon in any observation, and no observational evidence whatsoever supports the existence of a solid surface or material boundary in a black hole. All attempts to detect a boundary or material substance at the event horizon have consistently failed across multiple wavelengths and detection methods. Matter that approaches the event horizon does not accumulate or lodge there waiting to be observed by telescopes. It continues to fall inward and promptly vanishes from the observable universe, crossing the boundary without any obstruction or resistance. When an object, such as a star torn apart by tidal forces, A spacecraft on an unfortunate trajectory, or even individual particles like atoms or photons, passes the event horizon. It does so quite peacefully, with no resistance or collision at the horizon itself. There are no atomic collisions with any surface material, and no abrupt change in the physical structure of reality at that precise threshold marking the boundary. The fabric of space-time does not suddenly transform into something solid or impenetrable that would block passage. Instead, what truly changes at the event horizon is the set of possible paths that future events can follow in space-time according to the causal structure. The event horizon marks the boundary beyond which all paths, including those followed by light rays traveling at maximum speed and material particles moving at any velocity, lead inevitably inward toward the singularity at the center, as established by the geometry of general relativity and the solutions to Einstein's equations. The black hole's defining property is this one-way channel for causality. You may enter freely without hitting anything, but you cannot come back out under any circumstances or by any means. The error in the dense object idea also distorts how we imagine what happens to energy and information that falls into the black hole and crosses beyond the point of no return. If the event horizon were some layered structure composed of matter or energy fields, it could, in principle, store information in its physical composition, or even reflect it back outward in some manner that we could detect. But no evidence supports this picture at all from decades of observations. Instead, information carried by matter crossing into the black hole seems to vanish from external view entirely, raising deep and troubling questions about the fate of quantum information and leading to famous controversies over the so-called information paradox in physics that has puzzled theorists for half a century. Research continues to investigate whether something deeper preserves the information using quantum physics principles and mechanisms, with theorists proposing ideas involving quantum entanglement and Hawking radiation emitted from near the horizon. But the event horizon itself, contrary to the dense object image that suggests a material structure, does not store anything in a material sense or act as a repository for information. The persistent implication in the popular definition that black holes are objects also misleads our understanding of what we actually detect when we observe black holes astronomically using telescopes and instruments. Astronomers observe the indirect consequences of black holes and not any solid substance or material boundary that would reflect light or emit radiation. They see the gravitational effects on nearby stars, whose orbits reveal the presence of an invisible massive companion that must be a black hole based on its mass. They observe the bright emission from accreting matter just before it crosses over the horizon, as gas heats to millions of degrees in the swirling accretion disk and radiates intensely in X-rays and other wavelengths across the electromagnetic spectrum. More recently, they have imaged the shadow cast by the event horizon itself against glowing background of hot gas, as observed by groundbreaking projects like the Event Horizon Telescope collaboration in 2019, when they captured the first image of a black hole. But none of this radiation or indirect evidence comes from an actual surface or dense shell of material at the event horizon. Instead, it all comes from matter interacting with the intense gravity around the black hole and from processes occurring outside the event horizon in the surrounding space-time environment. The continued use of the word object inadvertently encourages a notion that is fundamentally out of step with modern gravitational theory and the predictions of general relativity that have been tested extensively. The black hole's reality is far more abstract than a simple material sphere floating in space. It is a region marked not by substance but by a boundary drawn by the rules of general relativity, where the curvature of space-time reaches such extremes that escape becomes impossible by the laws of physics. The event horizon is not an object in the everyday sense at all that we use for planets or stars. It is a place where space-time curves so steeply that nothing can travel outward, but no matter or energy forms the boundary itself or gives it physical substance. This distinction is not merely semantic or philosophical wordplay. It has real consequences for how we understand black hole thermodynamics, the behavior of quantum fields near horizons, and the ultimate fate of matter and information in the universe over cosmic timescales. As we move forward in exploring black holes and their properties, we will refocus the picture entirely, shifting from the misconception of black holes as things to the more accurate understanding of black holes as places in space-time. The black hole is not a thing sitting in space waiting to be touched or examined up close. It is truly a place, a profound region within the universe, whose meaning lies not in what it contains physically, but in what it forbids causally according to the structure of space-time. The event horizon forbids escape completely. It forbids communication from inside to outside the boundary. It forbids any trajectory that would carry matter or information back into the external universe where we observe. These prohibitions are encoded in the geometry of space-time itself, not in any material barrier or surface that blocks passage physically. Understanding this fundamental shift from object to place is essential for grasping the true nature of black holes and appreciating why they represent one of the most extreme and fascinating predictions of Einstein's general theory of relativity. Having clarified that the event horizon is not a physical object or dense material surface, we must now establish precisely what the event horizon actually represents in the framework of general relativity. The event horizon is fundamentally a geometric boundary in space-time, not a tangible structure made of matter or energy. Understanding this distinction requires us to think carefully about the nature of space itself and how gravity affects the path that objects and light can follow through the universe. The event horizon marks the ultimate point of no return, but it does so through pure geometry, rather than through any physical barrier that blocks passage or reflects matter and radiation back outward into the cosmos. In general relativity, space-time is not merely an empty stage where physical events unfold passively in the background. Instead, space-time is a dynamic entity that curves and warps in response to the presence of mass and energy, according to Einstein's field equations. This curvature determines how objects move through space and how time flows at different locations. Near massive objects like stars or planets, space-time curves gently, causing effects like the bending of light around the sun that was famously observed during a solar eclipse in 1919 and provided early confirmation of Einstein's theory. Near extremely compact objects like neutron stars, the curvature becomes much more pronounced, leading to stronger gravitational effects and more dramatic distortions of both space and time. When mass becomes concentrated in a sufficiently small region, the curvature of space-time becomes so extreme that it creates an event horizon. This happens when the escape velocity from the surface reaches the speed of light, which occurs at the Schwarzschild radius for a non-rotating black hole. For a black hole with the mass of our Sun, this radius is approximately 3 kilometers. For a supermassive black hole at the center of a galaxy with a mass of several billion solar masses, the Schwarzschild radius can be many billions of kilometers, comparable to the size of our entire solar system. The event horizon is a spherical surface at this critical radius, and it represents the boundary beyond which the escape velocity exceeds the speed of light. However, calling the event horizon a surface can be misleading if we imagine it as something physical, like the surface of a planet or a soap bubble. The event horizon has no material substance whatsoever. If you were to approach the event horizon of a sufficiently large black hole, one where tidal forces at the horizon are relatively weak, you would detect nothing unusual at the moment you crossed it. There would be no wall to hit, no membrane to penetrate, no sudden change in the properties of space around you that you could measure with local instruments. The space at the event horizon is simply empty space, vacuum containing no particles or fields that mark its location physically. What makes the event horizon special is not any local physical property, but rather its global causal structure in space-time. The event horizon is defined by the property that light rays emitted from it cannot escape to infinity. More precisely, it is the boundary of the region from which future directed light rays can reach distant observers in the external universe. Inside the event horizon, all future directed paths, whether followed by light traveling at maximum speed or matter moving at any velocity, lead inexorably inward toward the singularity at the center. This is not because something pulls you inward more strongly once you cross the horizon, although tidal forces do increase as you approach the singularity. Rather, it is because the structure of space-time itself has changed so fundamentally that the very concept of moving outward has lost its meaning. To understand this strange property, consider how we normally think about directions in space. In ordinary flat space-time far from any massive objects, we can point in any direction and in principle travel that way indefinitely. We can go up or down, left or right, forward or backward. Time flows in one direction only from past to future, but space offers complete freedom of movement in all 3 dimensions. Near a black hole, however, the extreme curvature of space-time causes these directions to mix and transform in ways that have no analogue in everyday experience. As you approach and cross the event horizon, what was originally a spatial direction pointing toward the center gradually transforms into a time-like direction. Inside the event horizon, moving toward the singularity becomes as inevitable as moving forward in time. This bizarre feature of black hole geometry means that asking how to escape from inside the event horizon is like asking how to travel backward in time. Just as you cannot avoid your future in ordinary space-time, you cannot avoid moving toward the singularity once you have crossed the event horizon. The singularity lies in your future just as surely as tomorrow lies in the future of someone standing on Earth right now. This is what physicists mean when they say the event horizon is a null surface in space-time. It represents a boundary where the causal structure changes fundamentally, separating the region where escape is possible from the region where escape is impossible by the laws of physics. The event horizon is also a one-way membrane in terms of causality. Events inside the horizon cannot influence events outside the horizon. No signal, no information, no causal influence of any kind can propagate from inside to outside. This is the origin of the famous black hole information paradox that has puzzled physicists for decades. If information falls into a black hole and crosses the event horizon, it appears to be lost forever from the perspective of the external universe. Quantum mechanics, however, insists that information cannot be truly destroyed, leading to an apparent contradiction between general relativity and quantum theory. Recent theoretical work, including ideas from string theory and the holographic principle, suggests that information may be preserved in subtle correlations in the Hawking radiation emitted by black holes over extremely long timescales, but the details remain controversial and actively debated. Despite being invisible and intangible, the event horizon has real physical consequences that can be observed and measured. The shadow of the event horizon can be imaged against the bright background of an accretion disk, as demonstrated by the Event Horizon Telescope in 2019, when it captured the first image of a black hole. The size and shape of this shadow depend on the mass and spin of the black hole, and agree remarkably well with predictions from general relativity. Furthermore, the event horizon plays a crucial role in black hole thermodynamics, a field that connects gravity, quantum mechanics, and thermodynamics in profound and surprising ways. The area of the event horizon is proportional to the entropy of the black hole, suggesting deep connections between gravity and information theory that physicists are still working to fully understand. The event horizon also marks the boundary where time dilation becomes infinite from the perspective of distant observers. As an object falls toward the event horizon, clocks on that object appear to tick more and more slowly when viewed from far away. At the horizon itself, time appears to stop completely from the external viewpoint. This means that from the perspective of someone watching from a safe distance, infalling matter never quite reaches the event horizon, but instead appears to freeze and fade away as its light becomes increasingly redshifted. However, from the perspective of the infalling observer, time passes normally, and the horizon is crossed in finite proper time without any local indication that something special has happened at that moment. Understanding the event horizon as a geometric boundary, rather than a physical object, is essential for grasping what black holes truly are. The event horizon is not a thing in space. It is a feature of space-time itself, a boundary drawn by the extreme curvature of space and time near a singularity. It contains only empty space, yet it marks the most profound boundary in the universe, the point beyond which escape becomes impossible, where the future leads inevitably inward, and where the causal structure of reality itself has been fundamentally transformed by gravity's overwhelming power in the cosmos. Having established that the event horizon is a geometric boundary in space-time rather than a physical surface made of matter or energy, we now arrive at the central insight that transforms our understanding of black holes entirely. A black hole is not an object in the conventional sense of the word that we use for stars, planets, or even clouds of gas. It is not a thing you could touch or a sphere of matter sitting in space waiting to be discovered by telescopes. Instead, a black hole is fundamentally a place, a region of space-time itself, where the laws of physics as we experience them have been pushed to their absolute limits by the overwhelming force of gravity. This conceptual shift from thing to place is not merely semantic or philosophical wordplay. It represents a profound reorientation in how we think about the nature of reality at its most extreme boundaries in the cosmos we inhabit. Consider for a moment what we mean when we talk about ordinary objects in the physical world around us every day. A rock is an object composed of atoms arranged in a crystalline structure held together by electromagnetic forces between electrons and atomic nuclei. A planet is an object made of rock, metal, and gas, held together by gravity into a roughly spherical shape determined by hydrostatic equilibrium. Even a cloud of interstellar gas, diffuse though it may be across light years of space, counts as an object because it consists of particles of matter occupying a region of space with definable boundaries. All these objects share a common feature that defines them. They are made of something tangible. They have substance, composition, and internal structure that can be analyzed and understood in terms of the matter and energy they contain within their volumes. A black hole defies this categorization completely and fundamentally challenges our notion of what constitutes an object in the universe. The event horizon, which defines the boundary of what we call a black hole and marks its size and extent, contains no matter, no particles, no energy fields, nothing at all. It is simply empty space, vacuum, indistinguishable in its local properties from the vacuum anywhere else in the universe far from massive bodies. What makes this region special is not what it contains physically, but how it behaves according to the laws of general relativity, how space-time is structured there by extreme gravitational curvature. The event horizon marks a boundary beyond which the geometry of space-time has become so warped and distorted that escape is impossible by any means. Inside this boundary lies a volume of space where all paths, whether followed by matter or light, lead inexorably toward the singularity at the center without exception. This is a property of the space itself and its geometric structure, not of any material substance filling that space or creating a barrier. This realization leads us to a more accurate way of thinking about black holes that aligns with the mathematics of general relativity. They are locations in the universe, volumes of space-time, places where reality has been fundamentally altered by extreme gravitational curvature. When we say that a black hole exists at the center of our Milky Way galaxy, we mean that there is a region of space there, roughly 17 million kilometers across, based on the event horizon radius corresponding to its mass, where the escape velocity exceeds the speed of light, and nothing can get back out to the external universe. We do not mean that there is a ball of matter 17 million kilometers in radius, sitting at the galactic center like a giant planet or dead star. The supermassive black hole at the heart of the Milky Way, known as Sagittarius A star, and observed extensively by astronomers, is a place defined by space-time geometry, not a thing made of material substance. This distinction becomes even clearer when we consider what happens to matter, that falls into a black hole from the perspective of both external observers and infalling observers themselves. According to general relativity, once matter crosses the event horizon going inward, it continues falling inward toward the singularity at the center along geodesic paths. The matter does not stop at the horizon or form a shell or crust or accumulate in any layer. It passes through the horizon as easily as you might pass through an imaginary boundary line drawn in empty space without any physical demarcation. From the perspective of someone falling in, crossing the event horizon involves no collision, no resistance, no physical barrier that blocks passage or signals the transition. You simply find yourself in a region of space where the rules have changed fundamentally, where all your possible future paths now lead inward toward the singularity, where returning to the outside universe has become as impossible as traveling backward in time according to the causal structure of space-time. The singularity at the center of the black hole, where general relativity predicts that density and space-time curvature become infinite according to the classical equations, represents a breakdown of our current physical theories. Most physicists believe that a complete theory of quantum gravity, which we do not yet possess despite decades of research, would replace the singularity with something less pathological and more physically reasonable. Perhaps it would be a region of extreme but finite curvature, or a quantum foam of space-time at the Planck scale, where quantum effects dominate, or some other structure we cannot yet imagine. But whatever the true nature of the singularity turns out to be, when we finally understand quantum gravity, it is hidden from external observation by the event horizon, protected by what physicist Roger Penrose called cosmic censorship in his fundamental theorems. The singularity does not define the black hole in an observational sense, or determine what we can measure. The event horizon does, and the event horizon is purely a feature of space-time geometry and causal structure. Thinking of black holes as places rather than things also helps us understand their behavior and interaction with the surrounding universe more accurately. When matter orbits a black hole, it is not orbiting around a solid object, like orbiting around a planet or star with a surface. It is orbiting through curved space-time, following geodesic paths determined by the gravitational field and the geometry encoded in the metric tensor. The closer the matter gets to the event horizon, the more extreme the curvature becomes, and the more dramatically space-time is warped from the flat Minkowski space-time of special relativity. At the innermost stable circular orbit, which exists at 3 times the Schwarzschild radius for non-rotating black holes, the curvature becomes so severe that stable circular orbits cease to exist. Inside this radius, any matter on a circular path will inevitably spiral inward and cross the event horizon within a finite amount of time. Furthermore, thinking of black holes as regions of space-time helps clarify the strange properties of time near the event horizon. As mentioned earlier, time dilation becomes infinite at the horizon from the perspective of distant observers watching from far away. This means that events occurring at the horizon appear to take infinitely long to unfold when viewed from outside, with infalling objects appearing to freeze and fade away as their light becomes increasingly redshifted toward infinite wavelength. However, from the perspective of the infalling observer moving through space-time along their world line, time passes normally, and the horizon is crossed in finite proper time. Inside the event horizon, the roles of time and space actually switch in a certain mathematical sense. The radial coordinate, which represents spatial distance outside the horizon, becomes time-like inside the horizon. Moving toward the singularity inside the horizon is as inevitable as moving forward in time outside the horizon, a consequence of how the metric components change sign at the event horizon boundary. The place versus thing distinction also illuminates why black holes have such strange thermodynamic properties that connect gravity to quantum mechanics and information theory. Jacob Bekenstein and Stephen Hawking showed in the 1970s that black holes have entropy proportional to the area of their event horizons, not their volumes as ordinary objects would. This suggests that all the information about what fell into the black hole is somehow encoded on the two-dimensional surface of the event horizon, rather than in the three-dimensional volume. This holographic principle has profound implications for our understanding of space-time and quantum gravity, suggesting that space-time itself may be emergent from more fundamental quantum information. None of this makes sense if we think of black holes as ordinary material objects, but it becomes more comprehensible when we recognize that black holes are regions of space-time with special geometric properties. Understanding black holes as places rather than things is essential for grasping their true nature and role in the universe. They are not cosmic monsters made of super-dense matter lurking in space to devour unwary stars and spacecraft. They are regions where space-time itself has been transformed by gravity into something qualitatively different from the rest of the cosmos, where the causal structure prevents escape, and where our understanding of physics reaches its current limits and demands new theories to proceed further into the unknown mysteries of nature. Having established that a black hole is a place rather than a thing, a region of warped space-time rather than a material object, we can now explore what would actually happen if you approached one of these extraordinary locations in the universe. The experience of approaching a black hole would be profoundly different from approaching any ordinary astronomical object like a planet or star. As you drew closer to the event horizon, the extreme curvature of space-time would create increasingly strange effects on light, matter, and the very fabric of reality around you. Understanding these effects requires us to think carefully about how light behaves in curved space-time and how the paths available to photons change as gravity intensifies near the boundary of no return. Imagine you are approaching a stellar mass black hole, perhaps one with 10 times the mass of our Sun, which would have an event horizon radius of approximately 30 kilometers. You're carrying a powerful flashlight, and as you descend toward the black hole from a safe distance far away, you shine the beam outward in various directions to see what happens. Initially, when you are still far from the black hole, the flashlight behaves normally. Light travels outward in straight lines, or more precisely along geodesics in the gently curved space-time, just as it would anywhere else in the universe. You can communicate with observers far away by sending light signals that escape to infinity without difficulty. The gravitational field is present and measurable, but it does not yet dramatically affect the behavior of light, trying to move away from the black hole. As you continue your journey inward, moving closer to the event horizon, something remarkable begins to happen to the light from your flashlight. The curvature of space-time becomes more pronounced, and this curvature affects the paths that light rays can follow through space. When you shine your flashlight directly outward, away from the black hole, the light still escapes, but it does not travel in a straight line as you might expect. Instead, the intense gravity bends the light's path, curving it in the direction of the black hole. The light eventually escapes to distant observers, but it follows a curved trajectory through the warped space-time, and it loses energy in the process, becoming redshifted to longer wavelengths as it climbs out of the gravitational well. At a certain critical distance from the black hole, you reach a region called the photon sphere. For a non-rotating Schwarzschild black hole, the photon sphere exists at precisely 1.5 times the Schwarzschild radius, or 3 kilometers in radius for a 10 solar mass black hole. The photon sphere is a spherical region where gravity is so intense that light can actually orbit the black hole in circular paths, going round and round without falling in or escaping outward. These circular orbits are unstable, meaning that any tiny perturbation will cause the photon to either spiral inward toward the event horizon or escape outward to infinity. Nevertheless, the photon sphere represents a critical boundary where the behavior of light changes fundamentally. Inside the photon sphere, light aimed outward will no longer escape to infinity. Instead, it will curve back around and eventually fall into the black hole. When you cross inside the photon sphere and shine your flashlight outward, the light from the beam becomes trapped in the intense gravitational field. Depending on the exact angle at which you aim the flashlight, the light might orbit the black hole several times before falling inward, or it might curve back immediately. But it will not escape. From the perspective of distant observers watching your descent, they would see the light from your flashlight becoming dimmer and dimmer as you approach the photon sphere, and once you cross inside it, they would no longer receive any light that you shine outward. You would appear to fade from view, not because you have crossed the event horizon yet, but because the light you emit can no longer reach observers far away from the black hole. As you continue falling inward from the photon sphere toward the event horizon itself, the situation becomes even more extreme. The light from your flashlight aimed in any direction now follows paths that curve back toward the black hole. There are no longer any outward trajectories for light rays, no paths that lead away from the event horizon to the external universe. The geometry of spacetime has become so warped that all future directed paths for light and matter point inward. You and the photons from your flashlight are inexorably drawn toward the event horizon, approaching it at an ever-increasing rate, as measured by your own clock, your proper time along your world line through space-time. Throughout this descent, you would also experience tidal forces, which arise from the difference in gravitational pull on different parts of your body. For a small stellar mass black hole, these tidal forces become enormous well before you reach the event horizon. The gravitational pull on your feet, which are closer to the black hole, would be significantly stronger than the pull on your head, stretching you vertically in a process that astrophysicists sometimes call spaghettification. Simultaneously, you would be compressed horizontally as spacetime curvature squeezes matter toward the radial direction pointing at the singularity. For a 10 solar mass black hole, the tidal forces would tear apart any human body long before reaching the event horizon, reducing it to a stream of atoms stretched along the radial direction. However, tidal forces scale inversely with the mass of the black hole. For a supermassive black hole with millions or billions of solar masses, like the one at the center of our Milky Way galaxy, or the one in Messier 87 imaged by the Event Horizon Telescope, the tidal forces at the event horizon are actually quite gentle. The event horizon of such a massive black hole is so large, billions of kilometers in radius, that the curvature there is relatively gradual. An astronaut could cross the event horizon of a supermassive black hole without being torn apart, experiencing only modest tidal stretching that would be survivable, at least temporarily, until they fell closer to the singularity where tidal forces inevitably become infinite. The view of the outside universe would also change dramatically as you approached the event horizon. Light from stars and galaxies behind you, in the direction away from the black hole, would appear increasingly blue-shifted and compressed into a shrinking region of the sky directly behind you due to relativistic effects and gravitational lensing. Light from regions to the side would be bent around the black hole, creating multiple distorted images of the external universe. You would see bizarre visual effects as light from distant stars takes curved paths through the warped space-time around you. The black hole itself would appear as a perfectly dark sphere blocking the stars beyond it, surrounded by a ring of light from photons bent around it in complex patterns that depend on the black hole's mass and spin. As you finally approach the event horizon itself, time dilation effects would become extreme from the perspective of external observers. Distant observers watching your descent would see your clock ticking slower and slower as you neared the horizon. They would see your motion approaching the horizon become increasingly sluggish, asymptotically slowing down, so that you never quite seem to reach it from their viewpoint. Your image would become dimmer and redder, as the light you emit becomes increasingly redshifted to longer wavelengths, eventually fading below the threshold of any detector, no matter how sensitive. From the external perspective, you appear to freeze at the horizon, taking infinite time to cross it, although in reality you cross it in finite proper time according to your own experience. From your own perspective, however, the approach to the event horizon takes only a finite amount of time as measured by your watch. For a 10 solar mass black hole, if you were to fall from rest at a large distance, you would reach the event horizon in a fraction of a second. For a supermassive black hole, the journey might take hours or days depending on your starting point, but the time is always finite, always measurable, and you do not experience any infinite time dilation yourself. Your own clocks tick normally from your perspective throughout the descent toward the mysterious boundary that marks the point beyond which escape becomes impossible in our fascinating universe. Having explored what happens as you approach the event horizon of a black hole, with light from your flashlight becoming trapped and space-time curvature intensifying around you, we now arrive at the most critical moment of the journey, crossing the event horizon itself. This transition represents one of the most profound boundaries in all of physics, yet the experience of crossing it would be surprisingly anticlimactic in certain respects. Contrary to popular imagination, you would not hit any matter or surface as you pass through the event horizon. There is no wall, no barrier, no physical boundary marking the transition from the outside universe to the interior of the black hole. The crossing would be smooth and continuous, more like stepping from one room into another than like breaking through a membrane or colliding with an obstacle in your path. The event horizon, as we have established, is not made of anything material. It is purely a geometric boundary in space-time, an invisible surface defined by the condition that the escape velocity equals the speed of light. When you reach this boundary, there is nothing to collide with physically. The space at the event horizon is simply vacuum, empty space that looks and feels locally identical to the vacuum anywhere else in the universe. If you were falling into a supermassive black hole with millions or billions of solar masses, where tidal forces at the horizon are relatively gentle, you might not even realize at the precise moment when you crossed the event horizon. There would be no sudden jolt, no dramatic change in your immediate surroundings, no alarm bell ringing to announce that you have passed the point of no return. This calm crossing stands in stark contrast to the dramatic depictions often seen in science fiction movies and popular media. The event horizon does not glow, does not crackle with energy, does not present any visible marker of its location to someone approaching it from inside the curved space-time. From your perspective, as an infalling observer, the laws of physics continue to operate normally in your immediate vicinity. Light still travels at the speed of light in your local reference frame. Clocks still tick at their normal rate. The fundamental constants of nature remain unchanged. What has changed is not the local physics, but the global structure of space-time around you, the set of possible paths you can follow into the future according to the causal structure encoded in the metric. The crossing feels calm in another surprising sense. Inside the event, a horizon can actually be quite bright, not the absolute darkness you might expect. This brightness comes from light that has fallen into the black hole from the outside universe along with you. Stars in the external cosmos continue to shine, and their light continues to propagate through space. Some of this starlight, following geodesic paths through the curved space-time, falls into the black hole and crosses the event horizon going inward. Once inside, this light illuminates the interior, at least for a brief time before it continues falling toward the singularity at the center. An observer who has crossed the event horizon would therefore see light from stars and galaxies that fell in before them, creating a potentially bright environment rather than total darkness. However, the view of the outside universe changes dramatically once you cross the event horizon boundary. Looking back toward the direction you came from, you would see the external universe compressed into an increasingly small region of the sky above you, appearing highly blue-shifted due to relativistic effects and gravitational lensing. Light from the outside continues to fall in through the event horizon, so you can still receive information about what is happening in the external universe, at least for a finite time. But the nature of this information flow is fundamentally one way. Light can enter from outside to inside, carrying information about external events inward, but no light, no signal, no information whatsoever can travel from inside to outside. The event horizon acts as a perfect one-way membrane for causal influences, allowing inward propagation, but absolutely forbidding outward propagation of any kind. This asymmetry in information flow has profound implications for the physics of black holes and leads to deep puzzles that physicists continue to grapple with today. The most famous of these is the black hole information paradox, first articulated by Stephen Hawking in the 1970s. The paradox arises when we consider what happens to quantum information that falls into a black hole and crosses the event horizon. According to quantum mechanics, information about the quantum state of a system cannot be destroyed. It must be preserved in some form, encoded in the correlations between particles and fields. However, according to classical general relativity, anything that crosses the event horizon is lost to the outside universe forever, with no way to retrieve the information it carried. Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon, radiation that we now call Hawking radiation in his honor. This radiation causes black holes to slowly lose mass and eventually evaporate completely over extremely long timescales, measured in many times the current age of the universe for stellar mass black holes. The problem is that Hawking's original calculations suggested this radiation is purely thermal, carrying no information about what fell into the black hole except for a few macroscopic parameters like total mass, charge, and angular momentum. If this were correct, then when the black hole finally evaporates completely, all the detailed quantum information about the particles that fell in would be permanently lost, violating the fundamental principles of quantum mechanics. Resolving this paradox has been one of the central challenges in theoretical physics for nearly 50 years. Recent work based on the holographic principle and the anti-de Sitter conformal field theory correspondence, known as ADS-CFT, suggests that information is actually preserved in subtle quantum correlations in the Hawking radiation. According to these ideas, the information about what fell into the black hole is somehow encoded on the event horizon itself, which acts like a holographic screen storing information about the three-dimensional volume in a two-dimensional surface. The radiation emitted by the black hole is not precisely thermal, but contains quantum correlations that encode the missing information, allowing it to escape back to the external universe over time. From your perspective inside the event horizon, however, these subtle questions about information preservation are not immediately relevant to your experience. What matters to you is that you have now entered a region of space-time from which there is no escape. All your possible future paths, every trajectory you could follow no matter how you accelerate or which direction you try to move, lead inexorably toward the singularity at the center of the black hole. The radial direction toward the singularity has become time-like rather than space-like, meaning that moving toward the singularity is as inevitable as moving forward in time. You cannot avoid it any more than you can avoid tomorrow arriving after today in the external universe. The time remaining until you reach the singularity depends on the mass of the black hole and your exact trajectory. For a stellar mass black hole with 10 solar masses, you would have only a tiny fraction of a second from crossing the event horizon until hitting the singularity, where tidal forces become infinite and your body is torn apart at the atomic level. For a supermassive black hole, you might have hours or even days of time remaining, falling through the vast interior volume toward the singularity deep at the center. During this time, you could still observe the universe, see light falling in from outside, and contemplate your fate, but you could not send any message or signal back to the outside world. The event horizon has become part of your past, a boundary you crossed but can never return through, much like yesterday has become part of your past and cannot be revisited. The calm nature of crossing the event horizon, stepping through an invisible boundary into a region of no return, underscores once again that a black hole is a place rather than a thing. You do not collide with an object. You enter a region where the rules governing possible futures have changed fundamentally due to the extreme curvature of space-time. Inside this region, brightness from infalling starlight may illuminate your surroundings briefly, but escape has become impossible by the laws of physics, and the singularity awaits inevitably in your future within the heart of this extraordinary cosmic phenomenon. Within the interior of a black hole, the very rules of space-time, time, and causality reach their most extreme limits. Having crossed the event horizon in the previous section, you are now in a radically unfamiliar domain where ordinary ideas break down. The fundamental barrier to reflection, messaging, or recovery of light from inside the event horizon arises not from the strength of gravity alone, but from how gravity warps the fabric of space-time until even the meaning of direction, especially the distinction between inside and outside, becomes permanently altered. In the space outside a black hole, you can shine a beam of light in any direction, and, as long as the direction is sufficiently away from the center, some portion of the light will escape to infinity, regardless of local redshift. Light can be reflected or bounced, sent along geodesics that wind out to the universe, and even returned if you use a mirror or another surface. Directionality is under your control. Once you cross the event horizon, though, the global geometry of space-time changes the options for light forever. Directionality and causality become fundamentally restructured. Now, every line, every extremal pathway a photon or any form of information might try to follow into the future inexorably points not outward but inward toward the black hole's singularity. Local experiments, whether using ultra-fast light beams or theoretical quantum probes, cannot circumvent this constraint. Inside the event horizon, the coordinate that measured spatial distance from the center, the so-called radial direction, now transforms into a time-like coordinate. The mathematics expressed in the Schwarzschild solution illustrates this. What appeared as a coordinate of space for external observers converts to a direction in time for infalling travelers. This means that progressing toward the singularity is as inevitable as the onward passage of time itself in the ordinary universe. Trying to reflect light outward is, in effect, trying to send light backward in time. Since the arrow of time only moves forward, and any motion away from the singularity would require a reversal of time, this is physically impossible. No force, no act, no ingenuity can circumvent the relentless order of causes and effects as dictated by the geometry of space-time within the event horizon. The tip of the light cone, which helps physicists illustrate all future possibilities for any event in relativity, tilts progressively inward with increasing proximity to the horizon and beyond. From outside, even close to the event horizon, it is still possible to aim signals outward. At the horizon, light cones tip so much that only signals moving exactly along the surface can remain there, and inside, the cones are so tipped that all possibilities for light or matter run toward the singularity. No path for energy exists that travels to the exterior once you are past the horizon. Every ray, even those fired at the maximum possible velocity and energy, races toward the black hole's ultimate geometric fate. Suppose you possess a perfectly reflective mirror and the most powerful flashlight available. Once you are inside the event horizon, you could aim the beam in any chosen direction, bounce it from the mirror as many times as you wish, but the result would still be the same. All rays are inevitably directed inward. The space-time itself determines these paths, not the nature or energy of your device. The space-time funnels every attempt to move outward toward a future that corresponds absolutely to movement toward the core. This effect illuminates why the idea of a black hole as an object is dangerously misleading. It is not about a physical barrier that absorbs or blocks, nor about a region where the laws of physics simply break for no reason. The event horizon's role is set by the geometry of space-time and the causal structures defined by general relativity. The causal past of any point inside the horizon includes only points within the black hole or on the horizon, never extending back into the wider universe. There is, therefore, no way for any event or signal that takes place within the black hole to affect anything outside. There is no outgoing light, no causality in the sense we understand it from the perspective of external observers. Extreme consequences follow from this absolute isolation. It is not only photons that are trapped. All forms of matter, energy, and even the fabric of information itself are dragged forward. All trajectories, both light-like and time-like, whether followed by particles or rays, end at the singularity. For the infalling observer, time seems to tick on as usual, and the nature of the trap is not immediately apparent. However, no matter what action is taken, communication with the outside is lost forever, and every attempt to send a signal back will result in signals that never reach outside the horizon to be detected. The singularity that lies at the core is, according to classical general relativity, a point or ring of infinite curvature and density where space-time ends. The laws of physics break down here, and all descriptions fail, except to say that whatever reaches the singularity ceases to exist in any recognizable form. No observer passing through the singularity can continue. It lies in the inevitable future of all who cross the event horizon. The fact that all future directed paths end at the singularity highlights again that the direction toward the singularity is, in every meaningful sense, a direction in time, not in space. Quantum theories propose that information may be preserved through mysterious mechanisms tied to the surface area of the event horizon or the properties of Hawking radiation. Yet, for the journeying observer, none of this changes the impossibility of sending anything outward. The causal structure means the only possible trajectories are toward the singularity. In every experiment, in every imagined scenario, no photon, particle, or field ever reverses course and escapes once beyond the horizon. This structure makes black holes unique in the cosmos and fundamentally distinct from every other object in the universe. Reflection, emission, signal transmission, recovery, and even memory as the outside world knows them, these are forever cut off upon entry. The geometry ensures that the inside is causally disconnected, not merely remote or hidden, but sealed by the flow of time and space toward the singularity. Thus, reflection back to the outside is not just difficult or unlikely, it is strictly forbidden by the deepest laws known. The event horizon, once crossed, fundamentally becomes part of your past in an irreversible way that resembles how yesterday slips permanently behind you in the ordinary flow of time. This finality is not simply a matter of distance or difficulty, as one might feel when travelling far from home on Earth and wondering about return. Rather, it is an absolute prohibition written into the geometry of space-time itself, a consequence of how mass and energy warp the universe so severely that certain directions cease to exist as possibilities for the future. Understanding this irreversibility requires grappling with the deepest insights of general relativity and quantum mechanics, and it highlights why black holes pose such profound challenges to our understanding of information, causality, and the ultimate nature of reality in the cosmos. Once you have crossed the event horizon, you can still observe light falling into the black hole from the outside universe, bringing you information about events that continue to unfold beyond the boundary you have passed. Stars shine, galaxies rotate, and the cosmic drama continues in the external universe. Some of that light, traveling along geodesics through curved space-time, crosses the event horizon after you do, and you can detect it with your eyes or instruments during the time remaining before you reach the singularity. In this sense, the outside universe is not completely cut off from you. Information flows inward through the event horizon, allowing you to maintain at least a one-way connection to the cosmos you have left behind. You are receiving data, seeing the universe as it was, learning about events that happened outside, even after your crossing. However, the reverse is absolutely impossible. You cannot send any information, any signal, any message whatsoever back out through the event horizon to the external universe. No matter how powerful your transmitter, how bright your beacon, how clever your encoding scheme, the information you try to send outward is trapped by the causal structure of space-time inside the black hole. Light you emit, radio waves you broadcast, gravitational waves you might try to generate through motion, all of these propagate inward toward the singularity along with you. None can escape. The event horizon acts as a perfect one-way membrane, allowing information to flow inward, but absolutely forbidding any outward flow of information or causal influence from the interior to the exterior. This asymmetry has profound implications for the concept of information in physics. In quantum mechanics, information is not merely data or knowledge in the everyday sense. It refers to the complete specification of a quantum state, including all the correlations and entanglements between particles and fields. Quantum mechanics is built on the principle of unitarity, which states that information is never lost or destroyed. Every process in quantum mechanics can, in principle, be reversed if you know the final state precisely enough. The time evolution of quantum systems is described by unitary operators that preserve information, ensuring that the past can always be reconstructed from a complete knowledge of the present. Black holes appear to violate this sacred principle of quantum mechanics. When matter and energy fall into a black hole and cross the event horizon, they carry quantum information with them into the interior. According to classical general relativity, this information is lost to the external universe forever, sealed behind the event horizon and eventually destroyed at the singularity where space-time itself breaks down. Stephen Hawking showed in the 1970s that black holes emit thermal radiation due to quantum effects near the horizon, radiation that causes them to slowly evaporate over extremely long timescales. The problem is that Hawking's calculations suggested this radiation is purely thermal, containing no information about what fell into the black hole, except for a few global properties like total mass, charge, and angular momentum. If Hawking's original conclusion were correct, then when a black hole evaporates completely, all the detailed quantum information about everything that fell in would be permanently erased from the universe. This would violate unitarity and fundamentally contradict quantum mechanics. It would mean that pure quantum states could evolve into mixed states, that information could be destroyed, and that the predictability at the heart of quantum theory would break down. This tension between general relativity and quantum mechanics is the famous black hole information paradox, and it has been one of the most important unsolved problems in theoretical physics for nearly 50 years. Recent theoretical work has made significant progress toward resolving this paradox, though many details remain controversial and actively debated. The key insight comes from the holographic principle and calculations based on the de Sitter conformal field theory correspondence, a theoretical framework that relates quantum gravity in certain spacetimes to quantum field theories without gravity. These calculations suggest that information is actually preserved in black hole evaporation, encoded in subtle quantum correlations in the Hawking radiation that accumulate over time. The radiation appears thermal at first, carrying almost no information outward, but eventually the quantum correlations build up and information begins to escape from the black hole in a highly encrypted form made possible by quantum entanglement. Researchers have calculated what is called the Page curve, which describes how the entropy of the Hawking radiation changes over the lifetime of an evaporating black hole. The curve initially rises as the black hole emits apparently thermal radiation, but at a certain point called the Page time, roughly halfway through the evaporation process, the curve peaks and begins to decline. This decline indicates that information is being released from the black hole, encoded in the quantum structure of the radiation in ways that are not apparent in semi-classical calculations. By the time the black hole evaporates completely, the total entropy of the radiation matches exactly what unitarity requires, suggesting that information has been preserved after all. However, these calculations rely on subtle quantum effects and on aspects of quantum gravity that we do not yet fully understand. Different theoretical approaches, including string theory, loop quantum gravity, and others, offer different perspectives on how information might be preserved and where it resides during the evaporation process. Some proposals suggest the information is encoded on the event horizon itself, which acts like a holographic screen storing data about the interior in a two-dimensional surface. Others suggest that quantum corrections modify the structure of the event horizon or the singularity in ways that allow information to escape. Still others propose more radical ideas, such as that black holes do not have true singularities, but instead have complex internal structures called fuzzballs that store information. Despite these theoretical advances, the fundamental mystery remains from the perspective of someone who has crossed the event horizon. For you, inside the black hole, escape is impossible. The event horizon has become part of your past, as unreachable as yesterday. You can observe the external universe through light that continues to fall in, but you cannot influence it, cannot send messages back, cannot warn others of your fate. Time travel would be required to reverse your journey, to move backward through space-time to a point before you cross the horizon. And time travel to the past is forbidden by causality and by the structure of space-time in general relativity. The singularity awaits in your future, approaching inevitably as you fall deeper into the black hole. For a stellar mass black hole, you have only fractions of a second remaining before tidal forces tear you apart, and you reach the point where space-time curvature becomes infinite. For a supermassive black hole, you might have hours or days, time enough to contemplate the strange fate that has befallen you, to observe the distorted view of the universe falling in around you, to ponder the mysteries of quantum gravity and information that physicists continue to debate in the external world you can no longer reach. The black hole, we have seen throughout this exploration, is not a thing but a place, not an object but a region of space-time transformed by gravity into something profoundly alien. The event horizon is not a surface but a boundary in the causal structure of the universe, a point of no return defined by geometry rather than matter. Inside this boundary, the rules change completely. Escape becomes impossible. Time and space exchange roles. The future points inexorably toward the singularity. And yet, through all of this strangeness, the laws of physics continue to operate, pushing the boundaries of our understanding and challenging us to develop new theories that can unite gravity and quantum mechanics in a complete description of nature.